So now people are talking about using language models to plan things. So it's no longer just a chatbot, but really help everyone do something useful.
This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Potker. Artificial intelligence technologies are accelerating research, expanding America's workforce, and transforming society as AI becomes a larger part of the world around us. Advancements in computer vision, natural language processing, and speech recognition have led to widespread use of learning-based systems in AI that interact frequently with humans in highly personalized contexts. Humans are using strategies such as reinforcement learning to train AI systems, and using AI systems to upskill the next generation workforce. We're joined by Mingyi Hong, a professor of electrical and computer engineering. His Optimization for Artificial Intelligence lab is designing solutions for problems in data science, machine learning, and AI. Professor Hong, thank you so much for joining me today.
Thank you, Nathan.
I want to ask you about reinforcement learning. What are some of the key components of this approach?
So reinforcement learning, or abbreviated as RL, is a branch of machine learning where agents learn to make decisions, right, by interacting with environments. So the key idea here is to learn through trial and error, guided by some kind of rewards, right? So therefore, the key components here are agents, right? So you have to have a learner, decision maker who is trying to learn. Environment, you're interacting with an environment. State, so the current situation you're in. Right? So describing what the environment is, and then your current position, and then what can you do, right? Actions. So a choice the agent can make at this particular time, and then reward, right? So after each action has been made, what are the sort of incentives or penalties that I receive, and then the policy, right? So policy is eventually what the strategy that the agents eventually learned.
What would be an example of a reward for a machine learning program?
All right, so let me give you give you an example of how this entire thing works, right? So for example, teaching a robot to walk. So this is a very typical machine learning problem where if you imagine you have a four-legged robot, it doesn't know how to walk at the beginning. It needs to learn how to walk across the room, right? So the robot doesn't know how to move initially, so it will just try out different sequences of movements, and then sometimes some may fail, some may not fail, right? So, but every time if it moves closer to its destination without failing, it'll receive a positive reward. Let's say +1 or good or something positive, right? If it tips over, it gets a penalty. So as you're gathering this reward, your sort of a model is trying to adapt, trying to optimize, trying to increase the reward. Oh, I see that I should do this, then I get better reward, then I should go towards that, right? So over time, using this kind of approach, trying and error, and then improving my model, so the robot will learn which sequence of actions leads to high reward, and then it will effectively teach itself to walk smoothly.
So you mentioned a robot there, but what are some of the applications that people might see around them that rely on reinforcement learning?
We all use the ChatGPT, right? So chatbot fine-tuning is a very sort of a very new but very important application for reinforcement learning. So here, what the model, now here the agent is the chatbot, what we're trying to train, right? So the chatbot may have seen a lot of text, maybe all the text on the internet, right? So it knows how to speak English, how to speak Chinese, or how to speak in Germany, right? So it knows the basic structure, but it needs to be aligned towards a particular way of human speaking, or particular region that some things could be said, some things are not appropriate, something appropriate, things like that, right? So it needs to be aligned towards a certain population, right? So this alignment process is basically learning from a reward model defined by this particular population. So this is a reinforcement learning problem. Think about alignment here as a process of training a language model to follow human instructions, right? Or to align to human preferences. So then the first question is, where is the reward model coming from? So we need to learn a reward model. So what people do is to collect, for a given question, you collect many answers. These answers can come from human, can from language model itself, and then ask human to annotate, to rank which one is the best, which one is good, which is not acceptable, and so on. And you collect thousands and thousands of data like this, right? And then use this data to train the reward model. Now, what does this reward model do? So this reward model hopefully will provide a good prediction of how good an answer is. Given a question, given a question answer, it will provide very high score if it is preferable, and this low score if it's not preferable. Right? So now with this reward model trained by human data, human annotation data, then we will sort of ask reinforcement learning, or we'll use reinforcement learning algorithm to align the language model itself. Okay, so before training, the language model already should know the basic structures of English, of Chinese, of Germany, whichever language you're working on, right? However, it doesn't know what should be the appropriate answer to certain questions. And then the language model will explore, right? Try to give it a question, just spit out whichever you want. The reward model will tell you, hey, this is correct, this is not correct, this is okay, and so on. With this signal, the language model will be trained to sort of tuning to be gradually going towards those that have high reward.
Is there a difference in using RL in large language models than you would in a chatbot?
This is the most popular way of sort of aligning or fine-tuning a chatbot, which is powered by large language model. So this is the most popular way. There are even harder, more advanced ways of using this. For example, now let's forget about chatbot, right? So let's just look at what large language model can be done, can be used to do. So now people are talking about using language models to plan things, right? So for example, as an agent, right? So I tell the language model to book a ticket for me, to book an air flight for me, right? So the language model needs to know, okay, here is the instruction. My first step is to go to this website, and then input this and that, and then get my results, and then look at my results and say, oh, this looks good. This flight looks good, and I'll pick this and go to Delta maybe, or go to some sort of a carrier's website, and then click, right, and then purchase and things like that. So it's a sequence of a planning step, and then you see here eventually you have a reward. Okay, you made the right decision, you made the wrong decision, and so on. And then the sequence is something that you can be how to plan this well, how the language model can plan this step by step by correctly calling the tools, correctly making decision at each step. Is also one very sort of exciting directions where RL, reinforcement learning, can be used to train language model. Right. So this is, of course, well beyond the chatbot.
Right. What are some of the limitations when you're getting RL into real world applications?
There are many limitations, I think, right now. So first of all, RL is very hard to train. Needs many millions of interactions to learn it effectively. So data is very hard to obtain, right? So this is one thing. The second is how to specify the reward. So designing good reward function is hard and often misaligned with the true human intention. Give you an example, right? So a cleaning robot is rewarded based on how shiny the floor looks, for example, right? So this is a reward function, right? Then the robot can sort of start to train this. Oh, certainly a certain time it discovered the shinier the better, I get better reward. Then what would it do? And then you will dump water everywhere to create a shine, but not actually cleaning. Not actually cleaning it, but just make it a shine, right? So this is happening because the agent simply try to maximize the reward, and the reward is not very well designed, right? So this is sometimes called reward hacking problem, and in practice, this is even for complicated task. This sometimes happen. Right? So this is a second sort of a challenge: how to design a better reward model, and the third is how to make the model more robust, make it safer. For example, for chatbot, chatbot learned so many things it has seen, right? It has been trained. So how to prevent it from saying something that is toxic, something that is not supposed to say, right? So this is very hard to distinguish. Maybe some of these answers can be very helpful. It directly answers what the human user was asking, right? For example, how to make a bomb, right? So then for a helpful agent, if it learns to be very, very helpful, it should directly say something detailed and so on, right? Which is obviously not appropriate. And then the last thing I want to say is sometimes, in many cases, the agent trained by RL lack generalization, which means that if you move to a new environment, the old policy may not work, right? So, for example, a robot may train to learn how to pick up a red cup from the table. Yeah, it learns well and everything. Now, if it move to a new environment where all the cups are blue, it may already forgot what to do.
This is where you run into that limitations of data. It's like it might know to do this part of it, but if it's this, what happens then?
Yeah, exactly.
Or like social norms, like maybe I wouldn't ask you about something like bomb reference there.
Yeah,
but like, how does it know that it's not supposed to tell you how to do this?
Exactly.
There's an opposite kind of concept here, inverse reinforcement learning. What's the difference between inverse reinforcement learning and reinforcement learning?
First of all, let me say that they're actually not the opposite to each other. So inverse reinforcement learning is something, let's say, one step beyond reinforcement learning. So some of our earlier discussion point to the discussion that designing reward model has been important. It's very hard and needs to be important. So inverse reinforcement learning goes one step beyond RL. So in RL, we need to have a reward model that guides me, right? For inverse RL, you don't. So instead of learning the policy from the reward, we learn the reward function itself by observing expert behavior, right? So the key difference here is that RL map, given a reward, I give you a policy. Inverse RL, give me expert demonstration. You don't tell me what is good or what's bad. Just demonstrate for me, right? And then I will learn the reward. I will try to understand, why you do this at this given point of time. You should do this, not that, and so on. And then with this, I eventually get a good policy. So that's the sort of key difference between IRL and RL.
What are some of the challenges in training an AI agent or algorithm to be an expert? Like, it seems like there could be a lot of complications in that.
One thing I think I just mentioned is data limitation, right? So high quality expert demonstration is very, very, very hard, very rare, especially if we're not considering just conversation. We consider something practical, something that really needs human demonstration. Like, for example,
like maybe the shininess of the floor from your robot example.
Or driving, right? So, for example, you want to teach an agent to drive, automated drive. So where is the data coming from? You have to go out and collect, probably take videos of how human drive and so on. So this data, this amount of data, is compared to the text data is being available online. So that's very, very small, right? Another important challenge here is really the ambiguity. It's also related to how we define the model, right? So how we define the reward model. You want to learn how to fly, let's say, right? So now you're observing, okay, how this pilot was doing. But then they will make very subtle adjustment when landing the plane. But you don't know where it is coming from. Is it because of a wind, because of the habit, or because of there's anticipation of something, turbulence, or something else, right? So this is very hard for the agent to understand. If you just look at, by observing the data, it's hard to sort of learn the reward. Also, another important thing is edge cases. So, for example, a chess grandmaster, you want to learn a chess game, how to play chess game. You're observing chess grandmaster that is sort of playing regularly. However, there will be some moves that are so rare that they only make it once or twice in their entire lifetime. but those are so important. Maybe it helps win the critical game, right? So those examples, those cases only happen once or twice. How should I learn? Right? There's not enough data. So those are sort of important examples, but it happens so infrequently. It's very hard to learn as well. So those are I think some of the main challenges, mostly related to data. Training a AI agent to be an expert.
The kind of a quality of data and the context almost.
Yeah, context. Yeah.
I'm thinking about, I had a conversation earlier this week where we were looking at vision language models, and I was kind of wondering, like, I don't have a question for you that it's percolating in my head right now, but I was thinking about how that might relate to this. How might a vision language model have a reinforcement quality to that training?
To train vision language model, I think reinforcement learning has already been applied, and it will continue to be very useful too. I think overall the idea is very similar. Now, vision language model, what gives to you is, so going back to the very first definition of reinforcement learning, right? So here, a vision language model compared with the only text language model give you more sort of context, right? So your environment is richer. You at a given position, you know what happens not only from the text, from the previous text exchange conversation, but also you know your actual position where you are, and then what context it is, right? And also the action space is much more complex. For vision language models, you're allowed to generate text, right? So you're allowed to reason. You're allowed to give a situation. The model is allowed to provide reason, to provide why you want to do this, and so on. It also will be allowed to click certain button, right? So you'll be able to sort of actually operate on some of the objects, right? So this gives you a much more complex action space as well. So entire training process will be more complicated compared with a text only language model, let's say.
Circling back to the IRL a little bit and thinking about workforce training, I know that, like, once you've established an expert model, how hard is it to introduce that to a novice human?
So you mean how human can use it?
So using it to train a human, like, so now you've got an expert to train the AI model, and now using it to turn a novice human into an expert. Like, what are the challenges in that, or have you seen that being put to use so far?
It's a very, very good question. Actually, this is related to some of the white papers we're writing just last month. I don't think there has been too much work on this, so that's why we try to propose those. I think if you want to train a human this way, it's better to integrate an entire process. Suppose you have an expert, right? Suppose you have an expert, and then suppose you have a teacher, and then suppose you have a human. Now, what the expert can do is to provide feedback, right? So what is good, what is bad? Now, the teacher teacher is also a model, right? So it's also an AI model. So the teacher's goal is not necessarily to become an expert, because the eventual goal is to teach human, right? So it needs to be able to integrate the expert's feedback and then ask the right question for this particular human. So it needs to understand what is the level of expertise at this particular point. What should be my next set of questions that I should ask, right? When I ask that next set of questions or next set of tasks, what is the human's feedback, the human's actual performance? And then I'll send to the expert to ask, hey, is it correct or what, right? And based on this, I will summarize these interactions and provide feedback to a human, and then provide next set of tasks. So I think a better way is to integrate the entire process, and then have this sort of a learning environment set up by sort of a training a teacher AI, teacher model, and to interact with the expert model. So I think that's better than that probably is a better way compared with directly interacting with the expert and say, hey, how should I learn from you?
I want to ask you about how NSF support has impacted your career. Can you talk about a little bit about the role grants have played for you?
I have been receiving an NSF grant start from my first year as an assistant professor. So over the years, I've been receiving grants for on topics related to optimization, designing optimization algorithms, and as well as for reinforcement learning. So obviously, you can see that optimization algorithm is an important very important component when we talk about how to train the model, how to improve the model. It all involves optimization algorithms, and also reinforcement learning technique has been a cornerstone for LLM, training LLM, and go beyond. So these are very crucial to support my lab's research, to recruit students, for me to attend conferences and so on. So I'm very grateful.
For my last question, I want to ask you about the future and what's coming up. Where do you see your work going in the next few years?
I think one of the most exciting frontier now is to use reinforcement learning to transform large language models into autonomous agent or systems of agent, where you could do multi-step reasoning to use and even solving scientific problems, right? So I think this sort of related to your previous question of what's beyond just chatbot, right? So I think these will be something that are really useful, will be really having significant impact to the society, to either scientific community or even beyond that, right? So here, as we alluded before, RL, reinforcement learning, will play a key role here, right? Because here we're essentially training the agent how to do planning, how to perform very complicated tasks. For example, the one of the goal here is to ask if language model can assist or plan or even execute a research workflow, right? So I have this. First, I can discuss with a language model. Hey, I want to do this. I have this idea? Is this good? Is it bad? And let's have a discussion. And then it will go on to do literature review. It will go on to do experiment design, analysis, writing paper, and so on, right? So this entire process, of course, will have human sort of supervision, but a language model itself or foundation model itself, maybe even go beyond language model, could be vision language model as well, can conduct the process step by step, right? Similar example, as I just mentioned before, booking travel and other things. So similar flavor, right? So it's no longer just a chatbot, but really help you do something, help everyone do something useful. So that's sort of the vision, and then I believe that reinforcement learning and also optimization here, how to update the model, how to optimize the model, will play an important role in this vision.
Special thanks to Mingyi Hong. For the Discovery Files, I'm Nate Podker. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.